Welcome to the lecture series on digital electronics 18EC 302C. In today's lecture, we are going to look at the working of the universal logic gates and also working of an XOR gate, and we are also looking at realization of these universal gates using basic gates, that is AND or NOT. So at the first we'll be looking at the NAND and NOR logic gates. So apart from the basic gates and are not, we also have two more logic gates, and they are called universal gates, NAND and NOR logic gates. So first we look at about the working of the NAND gate first. So NAND gates, so the name NAND comes from combining the operations of NOT plus AND. Or I can say exactly, the NAND operates like AND gate followed by NOT gate. That means on given two variables, we perform the AND operation first, and the result will perform the NOT operation. So AND operation means logical multiplication of the given variables, binary variables, and on the result we will perform the NOT or complementary operation. So performing these two operations in this sequence is equivalent to performing the NAND operation. So but this is done, these two operations are performed by a single circuit, and that circuit is called as NAND gate. And here we can see the logic symbol given for the NAND gate. So this is the logic symbol given for the NAND gate. So we can compare this logic symbol with that of the AND gate. You can see that there is an extra circle, small circle attached to this usual symbol of the AND gate. So placed after the AND gate symbol. So this small circle actually denotes the inversion or complementary operation of the result of this AND operation of the input variables. So here the input variables, so this logic symbol can be conceptually can be thought as an AND gate followed by a NOT gate. So here the same variables are given as input, the AB are given as input for the AND gate. The AND gate output is the logical multiplication of the input variables A and B. That is, the output of the AND gate is A dot B, or simply AB. So this AB is given as input for the NOT gate. So the output of NOT gate will be the complement of whatever input given to it. So here the input for NOT gate is AB or A dot B. The output of NOT gate will be AB bar or AB complement. So this combined operation of the AND gate AND operation followed by NOT operation is done by single circuit, and that is called as a NOT gate. So the exact logic symbol is given like this, but it can be interpreted, the operation can be interpreted as that AND gate is followed by NOT gate. And here the output of NAND gate denoted by a variable x, where x equals AB bar or A dot B bar. And the NAND gate operation working can be described by using a truth table also. So here the truth table shows on the left side, it shows the input variables A and B, and it also shows the various possible combinations of the input values. That is either A assumes 0, B can assume either 0 or 1, and when A assumes 1, then B can assume either 0 or 1. And for all these input combinations, the right hand side of the truth table shows the output of NAND gate, and here for a comparison, this also shows the output of AND gate also, which is if the input variables are AB, the output of AND gate will be A dot B or simply AB, and the output of the NAND gate will be the complement of the AND gate, so that is AB bar. So here the right hand side shows the output of both AND gate and NAND gate. So if we want only truth table of NAND gate, so we can ignore this column of AND. So this is just shown for here for comparison and convenience. So here we can obtain the output for each combinations of input in the truth table. When A is 0 and B is 0, you can see that the output expression, that is x equal to AB bar or A dot B bar, you can substitute in that A equals 0, B equals 0, so then that becomes x equal to 0.0 bar. 0.0 is 0 according to AND operation, and 0 bar is 1 according to NOT operation. So when both the inputs are 0, 0, both the inputs are 0, the output of NAND gate is 1. And similarly, when the input one of the input A equal to 0 and B equal to 1, then x equal to 0.1 bar. 0.1 is 0 and 0 bar is 1. So similarly, when A equal to 1 and B equal to 0, the output x equal to, it is 1.0 bar. And 1.0 is 0 and 0 bar is 1. So in this case also the output of NAND gate becomes 1. But see the last combination, when A equal to 1 and B equal to 1, so x equal to 1.1 bar. 1.1 bar, 1.1 is 1 and 1 bar is 0. So the output of NAND gate, when both the inputs are equal to 1, the output becomes 0. So here you can observe that the output of NAND gate is 0 only when both the inputs are 0, and only when both the inputs are 1. The output of NAND gate is low only when both the inputs are at high. Otherwise, in all other cases, the output of NAND gate is high. So that is what we have stated here. The NAND output goes low, that is 0, only when all of its inputs are high. That is the last case. Otherwise, the NAND gate output goes high. That means when any one of the inputs are 0, here it is A is 0, in this case B is 0, or both the inputs are 0, the output goes high. So this is all about the NAND gate, working of the NAND gate. So for operation performed, the logical operation performed by NAND gates is equivalent to performing AND operation on the input variables first, and then performing the uh, complement operation or NOT operation on the result and the output of the NAND gate. So here we have shown the two logical symbol of the NAND gate, and we have shown the truth table of the NAND gate, and here you can compare the output of AND gate and NAND gate for the same combinations of inputs. You can see that the NAND gate, whenever AND gate output goes low, the NAND gate output goes high, and whenever AND gate output goes high, the NAND gate output goes low. That is inverse operation. So since NAND means AND followed by NOT, whenever AND gate output becomes low, the NAND gate output becomes high, and vice versa. So next we'll look at one more logic gate, working of logic gate, that is NOR gate. So NOR gate operates like the operation of NOR gate. The NOR operates like a NOR gate followed by NOT gate. So NOR operation, and for NOR gate, the circuit performs an operation which is equivalent to performing the OR operation on the input variables first, and on the result will perform the complementary operation. So if we can look at the logic symbol of NOR gate, so this is the logic symbol of NOR gate. You can see that, compare this with the logic symbol of OR. There is only one difference, that there is a very small bubble, very small circle is there, and this small circle denotes the inversion. That means whatever the result of R, that you need to complement, or that you need to invert to get the NOR operation. So if the input variables are named as A and B, then the output of NOR gate, that is X equal to, can be written as A or B bar, or A plus B bar. So this is equivalent to an OR gate followed by an AND gate. So for OR gate, the inputs are A and B. The output of OR gate is A plus B. This is also the input given to your NOT gate, because the input is connected to output of OR gate. So the output of NOT gate becomes X equal to A plus B bar. So by this we can say that the operation performed by NOR gate is equivalent to performing OR operation first, followed by complement operation on the result of the OR gate. So we can explain the working of an OR gate by using truth table also. So in the truth table, on the left hand side, we have taken the input variables A, B, and all four combinations of the input variables. On the right hand side, we have shown the output of NOR gate, which is A plus B bar, and for comparison, we have also shown the output of OR gate, which is A plus B simply. And here we can obtain the output for each combinations of the input. So if you see the first case where A is equal to 0, B is equal to 0, Then the output of NOR gate, that is x equal to a plus b bar, if we substitute a equal to 0, b equal to 0, then x equal to 0 plus 0 bar, and 0 plus 0 is 0 according to OR operation, and 0 bar is 1. 0 bar is 1. So the output of NOR gate, we can say that it is 1 or goes high when the inputs a equal to 0 and b equal to 0. So similarly, if we take the second case where a equal to 0 and b equal to 1, then x equal to a plus b bar becomes 0 plus 1 bar, and this also equals to 0 plus 1 is 1, becomes 1 bar finally, and 1 bar is 0. So the output of NAND gate is 0. In the third case, a equal to 1 and b equal to 0, the output of NOR gate is becomes a plus b bar becomes, it is 1 plus 0 bar, and 1 plus 0 is 1, and 1 bar becomes 0. So the output of NOR gate in this case becomes 0. In the last case, when a equal to 1, b equal to 1, the output of NOR gate x equal to 1 plus 1 bar, and 1 plus 1 is 1, and 1 bar is 0. And here you can see that the output of NOR gate is 0 when both the inputs are 1. And by observing the truth table, we can say that the output is 1, the output of NOR gate is high only when both the inputs are low, and in any other case the output of NOR gate is low. So we can state the operation performed by NOR gate as: the NOR gate output goes low when any of the input when all of its inputs are low. The NOR gate output goes low when all of the inputs are low. I can say that so the NOR gate output goes low, that is these last three cases goes low when any of the input is high. So when any of the input is high, so in this case b is 1, this case a is 1, in the last case both a and b are 1. In all the three cases the NOR gate output goes low, and it goes high when all of the inputs are at low. So this is about the working of the NOR gate. And here we have seen that the NOR operation performed by the NOR gate circuit is equivalent to performing OR operation first, followed by performing the NOT operation on the result. And here we have shown the logic symbol where we have shown that it is equivalent to OR gate followed by NOT gate, and here we have shown the input and output relation between input and output relation for the NOR gate. So the next logic gate we are going to discuss is XOR logic gate. And here XOR logic gate, you can see that, so this is the logic symbol given for the XOR logic gate. And here we have shown only the XOR logic gate with two inputs. So this will be the one input and this will be the second input, and this is the output. So we assign the variables A and B for the inputs and F for the output variable. So here the logic expression given for the output of the XOR gate is AB bar plus A bar B, where A, B are the inputs for the XOR gate. So AB bar plus A bar B, and in short this output is given a notation that A mod B. So A XOR B. So we'll use this mod symbol, and this mod symbol indicates the XOR operation. So the working of this XOR logic gate can be seen by using the truth table. So here in the truth table we have shown the input variables on the left side A and B, and the output variable on the right side, that is F. And on the right hand side we have also shown all possible combinations for the input variables. And you can see that for all the combinations, for a particular combination we can obtain the output of the XOR logic gate by using the expression Boolean logic expression for the output of XOR gate, that is F equal to AB bar plus A bar B. So we will see when both the inputs are 0, A equal to 0 and B equal to 0, you can substitute these values for A and B in this expression, and then F can be read as 0 plus 0 dot 0 bar plus 0 bar dot 0, and this 0 dot 0 bar means 1. This becomes 0 dot 1 plus 1 dot 0. 0 dot 1 or 1 dot 0 is 0. So this becomes 0 plus 0. Then F becomes 0. So in this way we can obtain the output for the XOR gate for various combinations of the input. And so we are going to get, when both the inputs are 0, the output of XOR gate becomes 0. And when A equal to 0, B equal to 1, output of XOR gate becomes 1. And when A equal to 1, B equal to 0, we'll get output of XOR gate as 1. And when both the inputs are 1, we'll get the output of XOR gate as 0. XOR gate as 0. So by observing this, you can see that the output is high when the inputs are different. That is, when one of the input is 0, other input is 1. When one of the input is 1, other input is 0, then the output of XOR gate is high. And the output of XOR gate is low in two of the cases. two of the cases where in first case both the inputs are 0, or in the other case where both the inputs are at are 1. So the output of, so we can summarize the operation or working of the XOR gate, that the output of XOR gate is high when either of the input is high exclusively, that means the other input is 0. And the output of XOR gate is low when both the inputs are either 0 or 1 simultaneously, that is in the first case and last case. So this is the working of the XOR logic gate, and for this logic gate we have shown the symbol, logic symbol, and this is the Boolean expression for the output of XOR gate, A B bar plus A bar B, where it can also be sometimes expressed in short as A mod B. So this A mod indicates the XOR operation, and here we have also shown the working of the XOR logic gate by as a truth table. So this completes the explanation for all the logic gates. So in the previous lecture we have seen the three basic logic gates, and in this lecture we have seen the working of the two more gates, NAND and NOR, which are called universal gates, and we also seen the working of one more logic gate, that is XOR. So next we see why these NAND and NOR gates are called universal gates. So otherwise we can say that how to realize the basic operations, that is AND or NOT operations, using the so-called universal gates NAND and NOR logic gates. So why they are called universal logic gates, and how to implement the basic operations using these gates alone. So here we can see that so all Boolean operations that when write for the digital circuits or digital systems can be written, all Boolean expressions can be written by using combinations of the three basic operations and or. So any the function of any digital circuit, the output of any digital circuit in terms of its input variables can be expressed by using three basic operations: AND operation, OR operation, and NOT operation. So if you can implement these operations by any other gate, so any Boolean expression we can say that can be implemented by using a combination of AND gate, OR gate, and NOT gate. So here not only this, and when we come to this NAND and NOR gate, we can see that the NAND gate can be used, that means a number of NAND gates can be used in proper combination to implement any of these three basic operations. That means the number of NAND gates can be combined to perform AND operation without using AND gate. Number of NAND gates can be used alone to get OR operation, to perform OR operation on the input variables without using OR gate. And the number of NAND gates can also be used to perform NOT operation without actually using NOT gate. And this we will be calling as realization of these operations using NAND gate. And since only to implement any Boolean expression, only these three operations are required, and since these three operations can be implemented by using only NAND gates, the NAND gate is called as a universal gate. And the similar case is with the NOR gate. So the NOR gate can also be used in proper combination to implement many of the basic operations. So that is why NAND and NOR gates are called universal gates. So finally we can say that any Boolean expression can be implemented by using either NAND gates or NOR gates alone. So to implement any Boolean expression by using these gates alone, first we have to see how to implement the basic operations by using NAND gate alone or NOR gate alone. So we'll see in the next slide how we implement these basic operations by using either NAND or either NOR. So this slide shows how only a combination of NAND gates can implement the NOT operation, AND operation, OR operation. And similarly, how a combination of NOR gates can implement all the three basic operations. So in the first place, we'll start realizing the three basic operations using NAND gate or gates. So if you take a NAND gate, a 2-input NAND gate, and if you tie the second input to the first input of the NAND gate, and the second input is tied to the other input. So that means only you can give one input. Only you can give one input. So here you consider that input as the input variable A, and then what will be the output of the NAND gate. So by using the regular expression, Boolean expression of the NAND gate, x equal to, when there are two inputs A, B, the regular expression for the NAND gate becomes x equal to A dot B bar. And here the second input is also tied to the first one. So both the inputs are A only. So then x equal to A dot A bar. And A dot A is A only. So then the output becomes x equal to A bar. So that means output is A bar, input is C. So this circuit, I can say it performs NOT operation. So I can say that when NAND gate is this way, it means when the two inputs are same, the NAND gate performs the NOT operation or complementary operation, and I can say that the NAND gate is equivalent to inverter or NOT gate. So an AND gate is equivalent to a NOT gate when both of its inputs are same. When both of its inputs are same. So this is how we can use an AND gate to perform the NOT operation. And similarly, so in the second case, here we have used one NAND gate, first NAND gate, and the inputs are given as AB. And the output of this NAND gate is A dot B bar, or simply it is AB bar. And if we can apply this output to an AND gate, then the output of NOT gate will be AB simply. So when the inputs are A and B, the output is AB, that gives you AND operation. And you can see that, so we have already seen how to implement the inverse operation by using NAND gate alone. That means the two inputs must be same. So if we give the output of this NAND gate to the AND gate, for the both inputs of AND gate, then the output of this NAND gate, second NAND gate, becomes the inverse of its input. So its input is AB bar and the output is inverse of this, that means AB bar bar. And when there is a double complementation, the complementation cancels and we'll get original variable, which is AB. So here the overall output is A dot B and the input is AB, and this overall operation is equivalent to the NAND AND operation. So here we can say that this is equivalent to NAND gate, or I can say that when NAND gates are connected this way, it performs the AND operation. Similarly, we'll go with the third circuit, where we can see that here we have used the NAND first NAND gate, and we have given A as input for both the inputs of the first NAND gate. So then the output, so then this NAND works as performs the inverse operation, complementary operation. So the output will be A bar. And for the second AND gate, we have given both the inputs as B. So it also performs the inverse operation. So the output will be B bar. And these two outputs are given as input for the third NAND gate. So the output of this third NAND gate becomes X equal to A bar dot B bar bar. So this by using certain theorem called De Morgan's theorem that will be discussed later. So this output X equals to A plus B, and you can see that the overall output is A plus B for the inputs AB. That means this overall circuit performs the OR operation. So or I can say that when NAND gates are connected this way, they will perform the OR operation. This entire circuit is equivalent to OR gate. So that means instead of using three different gates, we can use a single gate, one type of gate called NAND gate, and combinations of the same gate can be used to obtain used to perform different operation performed by different gates. So here we have realized the NOT operation, AND operation by the second circuit, and the OR operation by the third circuit by using only NAND gates. So this is we call the realization of the AND or NOT operation by using NAND gate. And in a similar way, we can implement or realize the three basic operations using OR gates also, NOR gates also. So if you take the NOR gate, and if for the two inputs, if the two inputs are same, the input is indicated by A, then the output of NOR gate becomes X equal to A plus A bar, and A plus A is A and becomes A bar. You can see that the output is the inverse or complement of the input, and you can say that the NOR gate, when used this way, that means when both the inputs are same, it performs the NOT operation. So I can say that the NOR gate connected in this way is equal to NOT gate. And similarly, you can see the second circuit. So here we have taken the first NOR gate. The inputs are A and B. The output of NOR gate 1 is A plus B bar. And you can see that when this is given as input for the NOR gate, you can see this complement goes away and the output becomes A plus B. So this is the result of OR gate. So that means we can obtain our operation. and this can be done uh, by by connecting this output to the input of NOT gate. So, but instead of using NOT gate, we have already realized NOT operation by using NOR gate. So this output is given as input for both the inputs of NOR gate. So then this NOR gate performs the inverse operation of its input A plus B bar bar. So that two complements cancels away. So this results in A plus B. So we can see that the overall output is A plus B for the inputs A and B. That means uh, this combination of two NOR gates performs the OR operation. You can say that this circuit is equivalent to a single OR gate. And you can also see the third circuit where we have used we have given uh, the same input A for both the inputs of the first NOR gate. The output becomes A bar since this X performs complement operation. Similarly, we have used a second NOR gate for which both the inputs are B, so the output is B bar, and these two outputs are given as inputs for the third NOR gate, and the output of this third NOR gate X equals to A bar plus B bar bar. And by using the De Morgan's theorem, this equals the output equals A dot B, and you can see the overall output is A dot B, which is the AND operation between the two input variables. So we can say that this circuit, which contains only NOR gates, performs or implements or realizes AND operation. So this entire logic circuit is equivalent to an AND gate. So here also we can see that NOR gate, when used in proper combinations, can perform NOT operation, can realize NOT operation or OR operation and AND operations. So since either NAND or NOR gates alone can realize all the three operations, they alone can use to implement any Boolean expressions. So these two gates are usually called as universal gates. So this completes the lecture, and in this lecture we have discussed the working of NAND and NOR gates in detail along with their logic symbols and truth tables, and we have also discussed working of XOR gate along with the logic symbol and truth table, and we have also shown uh, how to implement the basic operations using either only NAND gates or only NOR gates, and by this we complete the lecture.